my KCET 2026 aspirants, so welcome to Sankalp batch, and today we are in the electrochemistry part 2 lecture. Okay, so in today's class what all topics we have? So in today's class we will be seeing electrochemical series and Nernst equation. Okay, so last class we have discussed something about reduction potential and all, so we will be talking about these two topics in detail today. Before that, moving to the, so these are part 3, part 4 and part 5 which we will be seeing, and before moving today's class, let's solve some questions that we have discussed on the last class. Okay, so the first question here we have is, electrochemistry deals with, so all of you please put down in the comment section quickly, interconversion of chemical and electrical energy, interconversion of mechanical and chemical energy, conversion of chemical energy to mechanical energy, conversion of spontaneous chemical change into non-spontaneous chemical change. So very clearly we have discussed it is for conversion of chemical energy to electrical energy. Okay, interconversion. Next, question number 2. Yes, so which of the following is true about electrochemical cell? Okay, so electrochemical cell, as I told you, we have two types, right? One is your galvanic cell and one is your electrolytic cell. Okay, but generally this galvanic cell is sometimes also called as electrochemical cell. Okay, so here when it is asked, it is for your galvanic cell. Okay, so now oxidation occurs at cathode. So I have given you a mnemonic, if you remember, lone, right? So what does lone stands for? Left. On the left side you have oxidation, then you have anode, and on anode we have negative charge, right? So oxidation occurs at cathode? No, oxidation occurs on the anode. So this is a wrong statement. Then reduction occurs at anode? No, reduction occurs at cathode. Next, electrons flow from anode to cathode. So if you have remembered, if I have shown you the Daniel cell, we had here zinc rod. Okay, Zn2 plus came out and electrons were released here, and these electrons moved out and then these electrons were collected, and here copper 2 plus gained these electrons and deposited as copper. So electrons generally will move from anode to cathode, so that is why this is correct. Electrons flow from cathode to anode, that is wrong. Okay, next we have which one of the following is an incorrect statement for an electrochemical cell? Again, when it is mentioning electrochemical cell, consider it as an galvanic cell. Okay, so the oxidizing and reducing agents should be separated from each other. No, see, when I have this one, if you have in one rod, you have Zn and Zn2 plus, right? Zn is the rod and Zn2 plus is the, in the solution we have Zn2 plus. So Zn gives Zn2 plus by losing 2 electrons. So this is your oxidized form and this is your reduced form. So they are with together each other, they are not in the separate compartments, right? Oxidized and reduced species should be together, and if you can see, Zn is your oxidizing agent, Zn2 plus is your reducing agent. So this is a correct statement. Okay, sorry, you have to find, should be separated, the oxidizing and reducing agent should be separated from each other. So this is incorrect. Okay, this statement is incorrect, so that is why option A can be the answer. Next, if an external potential is applied in the cell, thus decrease slowly and the reaction stops. Yes, this is absolutely correct. The cell stops working after some time. This is also correct because after some time the concentration, the Zn and the copper concentration keeps on decreasing, so the cell will stop working. The circuit is completed externally by connecting wire. Yes, that is also correct. So incorrect statement is option number A. Moving to the fourth question, the electrochemical cell stops working after some time because the electrode potential of both the electrodes becomes 0. No, the electrode potential is a standard electrode potential, it does not become 0. The electrode potential of both the electrodes become equal. Yes, after some time what happens, since the concentration keeps on changing, the electrode potential of both of them becomes equal. And if you remember, current can only flow when there is a potential difference, but when both the electrodes potentials are equal, at that time equilibrium is reached, and at that time the cell stops working. Okay, One of the electrode is away, none of this, these are not the correct options. Next, the study of electrochemistry is mainly depend on the concept of endothermic, exothermic. No, it is because of redox reaction. Okay, the chemical reaction which we are talking about, the chemical energy which we are talking about is from the redox reaction. Next, the main function of the salt bridge is to allow ions to go from one cell to another. The ions do not move from one cell to another. To provide a link between two half cells, yes, this is also a function. To keep the EMF of the cell positive, no. To maintain the electrical neutrality of the two half cells. So both B and D are actually correct, but if you can find main function, okay, the main function of the salt bridge is to maintain the electrical neutrality of the solution in two half cells. Moving to the next question. The most important condition for the galvanic cell is the electrode should not have physical contact. The electrolysis should be done in a separate container. The electrode should be inert. The two half cells should be connected internally by some device. So the electrodes should not have physical contact. No, we can have physical contact. The electrodes are in physical contact with the electrolytes. So that is not there. The electrolysis should be done in separate container. First of all, there is no electrolysis taking place here. The electrode should be inert. No, we can have reactive inert electrodes also. The two half cells should be connected by some internal device, and that internal device is your salt bridge. Right? Okay. Moving to the next question. The cell is given is best represented by. This is a good question. You can see Zn is undergoing what? Oxidation. And Ag plus is undergoing reduction. So we have left side is always oxidation. So I will write Zn undergoing oxidation. Then you have salt bridge and silver undergoing reduction. Right? So which is this option? Option number B. So this is completely wrong because Zn is shown on the reduction side or on the right hand side. So Zn should be on the left hand side, and this 2 will not be required. So that is why option number D is incorrect. Next, the potential difference between the metal electrode and the solution around it under equilibrium is called as electrode potential, right? Yes. Next, the standard EMF of the following cell is, okay. So the standard EMF of the following cell, you can see copper is there and silver is there. This side definitely is anode and this side is cathode, right? So what is E of the cell? Or standard E naught of the cell is equal to E naught of cathode minus E naught of anode, right? This is there. Then what is the standard potential of copper? So which is your cathode here? Anode is copper and cathode is silver, okay. So if the standard potential of the copper, which is your anode, okay, is 0.337 volt, what is the standard potential of the Ag electrode? So I can write here E naught of Ag plus 2 Ag minus E naught of copper 2 plus 2 copper, okay. So what is the value of E naught of the cell is given? 0.463, okay. Then we have X, which is silver, I have to find out, and this is 0.337. Okay, so now if I solve this, you have to just add this one, 463 plus 337. So you will have plus 0.8, which is your option number B here. Okay, fine. So now we will come to today's lecture, that is electrochemical series. Now what is electrochemical series? It is defined as the arrangement of electrodes with the half cell reaction in order of the decreasing standard cell potential. So you have different electrodes, their reduction potentials are given in the decreasing order. Okay, so let me show you. You can see here, I hope this is visible. Yes, you can see here we have F2 2.87, 1.81, 1.78. So the decreasing value of reduction potential is called as your electrochemical series. Now why do we need this? What are the applications of electrochemical series? The first one is definitely to calculate the EMF of the cell. So for example, I want to know the, so this one, if you see, it is E naught of silver minus E naught of zinc, right? So I need the value of the silver and zinc that I can get from the electrochemical series. Next application what I have, to predict the relative strength of oxidizing and reducing agents. This is very, very important. The more positive value. So if E naught value is very high, for example, if you see we have this F2 E naught value is 2.87. It is a very high value. 2.87 is the E naught value, positive value, which indicates that F2 can undergo reduction very easily. Okay, reduction potential is high. That concludes that F2 can undergo reduction very easily. If F2 is undergoing reduction easily, then it will behave as a very, very strong oxidizing agent. Okay, or it is having good oxidizing power. So I can say that more is the reduction potential, better is the oxidizing power. Okay, and vice versa. So I have here the second option. The more positive E naught value will be, the better will be the oxidizing agent or oxidizing power. Let's see the third application, to predict the feasibility of the reaction. So when you calculate this E naught of the cell, if the E naught of the cell comes out to be positive, then the cell reaction is feasible, or that cell will undergo, or that cell reaction will take place. Okay, so you should be knowing that. Next we have to predict if a metal will react with acid to give H2 or not. This I have discussed in the last class, the copper and the zinc case, right? If the reduction potential is more than 0, then hydrogen gas will not be liberated. If the reduction potential is less than 0, then the hydrogen gas will be liberated. Let me explain this once again. So you can see here, see, hydrogen reduction potential. Okay, this is the reduction reaction of hydrogen, okay, which is equal to 0. If I have copper reduction potential, its reduction potential is 0.34 volt, right? Now suppose what I'll do is, you have copper 2 plus and you have HCl. Okay, this reaction is there. Now what happens? Any metal, so copper is reacting with a metal, so I'll just take copper here. Yes. So now what happens? There is a tendency for copper to get reduced, and there's a tendency of H plus to get reduced. For example, just let me write down, this one is CuCl2. Okay, so copper is in +2 state, here H is in +1 state, right? So what will happen? What can happen here? You can see that copper has the tendency to get reduced, hydrogen also has the tendency to get reduced, but copper reduction potential is maximum, so copper will get reduced and hydrogen will not get reduced. So if copper will get reduced, you will get copper here. Since hydrogen is not getting reduced, it will remain as H plus. You cannot get H2 gas there, right? So if the reduction potential is more than 0, then hydrogen gas is not released. If the reduction potential is less than 0, then the hydrogen gas is released. So any metal placed below the hydrogen, so hydrogen is 0, below that will be negative value, is a strong reducing agent and can reduce H plus from acid to H2. Why we are saying that it is a strong reducing agent? So what happens? Below hydrogen, whatever is there, they all have negative reduction potential. Okay, below hydrogen we have negative reduction potential. So let me just show that one to you. You can see here, where is hydrogen? Yes, here there is hydrogen. Below hydrogen we have lead. Okay, lead reduction potential is -0.13. That indicates that lead is not having the tendency to undergo reduction. That means it has a tendency to undergo oxidation. So -0.13 means reduction is very difficult for lead. Difficult is reduction, but easier will be oxidation. So lead will try to undergo oxidation. If it is undergoing oxidation, it will behave as a reducing agent. So that is why we have here the statement that I told you that fine. So here I told you that that is a very good reducing agent. Why? Because it tends to undergo oxidation. Below 0 or below hydrogen, the elements have negative reduction potential. Negative reduction potential means they are not interested in undergoing reduction, they are interested in undergoing oxidation. Okay, so if oxidation is undergoing, that means the nature will be what? A very good reducing agent, and they can reduce the hydrogen to H2. Okay. Third one, to predict if a metal can displace another metal from its salt solution. So this we have studied in class 10 also, reactivity series, right? So if a metal is having, so or any metal placed below in the series will displace all the metals which are placed above it in front in the form of solutions. Okay, so that means if you see here, let's go back. So lithium is the one which is lowest, right? So lithium can replace all these metals from this salt. Potassium can replace all the metals above it. Calcium can replace all the metals above it based on their reactivity series. Okay, fine. So we have got this one. Next we'll talk about Nernst equation. Okay, so what is basically Nernst equation? First of all, you should know that we are able to calculate the EMF of the cell. The formula we are using here is E naught of right minus E naught of left, or E naught of cathode minus E naught of anode. But remember, this formula is applicable only if the electrolyte's concentration is 1 molar or unity, but that is not possible every time, right? So you can see Nernst equation gives the relation between the EMF of the cell and the concentration of the reactants and products under a given set condition. Till now we have assumed the concentration of all the species as unity, but this is not true always. We cannot have every time the concentration to be 1 molar. So in those cases, Nernst equation helps us to calculate the cell EMF. Okay, how we are using that we will see. Okay, so Nernst equation can be written for two types. One is for only electrode and one is for the complete cell. When I am talking about only electrode, means I am talking about, for example, I have N plus, it gains N electrons to give M, right? So this is what is your one complete electrode, its Nernst equation if you want to find. So that will be equal to E naught, okay, what is the general value? E naught minus RT by NF, okay, this is the formula, RT by NF log of product by reactant. So I have M, and in the reactant I have N plus, okay, product by reactant. Now here you should be remembering that solid metals concentration is taken as 1. So that means this becomes 1 and then this becomes RT by NF ln 1 by Mn plus. Now this is not the simplest form, we can simplify it further. So what happens, I can write E is equal to E naught minus, if I convert it into log, I will get 2.303 RT by NF, okay, 2.303 RT by NF. So I can then that if you further simplify, you will get 0.0591 by N log of 1 by the concentration of the metal ion. Okay, so this is the formula for a single electrode. If you have the complete cell, the same thing. In this position, what will happen? You will be taking the product ions divided by the reactant ions. Okay, that is the only difference. Here you will have 1, here you will have product and reactant concentration. We'll discuss this in detail. So let me show you this reaction. You can see I have Zn plus Cu2 plus equal to Zn2 plus U. E of the cell is equal to E naught of the cell minus 0.059 by N. What is this N here? So, okay, before that, let me just introduce all the terms here first of all. So, N is what? N is the number of electrons. Please write down, N is the number of electrons. Then you have R. R is gas constant. Okay. T is what? Temperature. Okay. So, substituting 2.303 R and T and this Faraday is what? 1 Faraday is equal to 96500 coulombs. Okay, by substituting all these values we get 0.0591 here. That is a simplified form. So only thing you need to be worried about is N, which is the number of electrons involved in that particular reaction. So if I show this next reaction, Zn to Zn2 plus 2 electrons are involved, copper 2 plus 2 copper 2 electrons are involved. So I have E of this equal to E naught minus 0.059 by 2, which is your N, log of product ions Zn2 plus divided by reactant ions. Okay, here certain things you should know that So I can say now this E of the cell depends on the concentration of both Zn2 plus and Cu2 plus. Okay, so if I increase the Cu2 plus value, then what will happen? This fraction will decrease, and if this fraction is decreasing, you are subtracting a smaller number from E naught of the cell, so E of the cell will also increase. So it increases with the increase in the concentration of Cu plus ions. So just once again you can listen, when you are increasing the concentration, when denominator is increasing, the whole fraction will decrease and overall this number will become a smaller number. I am subtracting a smaller number from E naught of the cell, so this value will be increasing. If you are increasing Zn2 plus value, Zn2 plus value you are increasing, that means this fraction value will increase. As a result, a bigger number will be there and you are going to subtract a bigger number from E naught of the cell, as a result of which the E of the cell will again decrease. Let me give you an example here. For example, see, just a minute. Okay, so I have, this is the value, okay, E of the cell equal to E naught of the cell 0.059 by 2 log of, I have Zn2 plus by copper 2 plus. Okay, let this E naught value be 5, okay, or let me, yeah, 5. Now what happens, you are increasing this value, okay. When you increases the copper 2 plus ion concentration, the denominator is increasing, this whole fraction will decrease, and when I multiplied everything, I am getting the number for example 2, right. So I am subtracting 2 from 5 and that gives me 3. Okay, this is one scenario. Now what happens, you are increasing the concentration of Zn2 plus. If you are increasing the Zn2 plus, this whole value will increase, overall this number will increase. You are going to subtract a bigger number from E naught, so let this value comes here as 4, okay, and because you have increased the numerator concentration, this bigger number is 4. Now if I subtract, I will get 1. So you can see that the E naught value, E value here is 3 and here is 1. So I can say that if I increase the copper concentration, E naught value will increase. If I increase Zn2 plus concentration, E naught value will decrease. Okay, so that is what I have given here. So now what we can do is, we will write for this one exactly, I will write the Nernst equation for this one. So you just have to take product and product ions divided by reactant ions and the number of electrons involved there. So I can write E of the cell here will be equal to E naught of the cell minus 0.059 by, here Ni to Ni2 plus, I have 2 electrons. Ag plus to Ag is actually 1 electron, but you can see you have 2 Ag here. So 2 Ag will have 2 electrons, so that is why it is 2 log of product Ni2 plus concentration divided by reactant concentration, that is Ag plus. Okay, here one more thing that you should keep in mind is Ag plus, in front of Ag plus you have a 2 there, right. So that 2 should also be present as a power. Okay, so whatever is present in the stoichiometric coefficient, that has to be present in the power. Okay, so for example, if I have, this is the equation, so how can I write here, E of the cell equal to E naught of the cell minus 0.0591, number of electrons here involved is n. Okay, then you have log of product concentration, C to the power of C, D to the power of D, you have A to the power of A and B to the power of B. Getting? Fine. Next, we'll talk about equilibrium constant here. Okay, so generally what happens, as we see when the reaction keeps on proceeding, okay, so Zn2 plus ions are forming more and more, right. So the Zn2 plus ion keeps on increasing and copper 2 plus ion keeps on decreasing, right. That's the tendency that is continuing. So after a certain time what happens, the voltage of the cell keeps on decreasing. So if you remember, Zn2 plus concentration is increasing, copper 2 plus concentration is decreasing. So this will overall lead to the value of potential difference decreasing. Why? Because we have this equation, right, E equal to E naught of the cell log of Zn2 plus copper 2 plus. So if Zn2 plus increases, E naught, E of the cell will decrease, and if copper 2 plus decreases, then also this will decrease. So this E of the cell continues to decrease. After some time what happens, there is no change in the concentration of Cu2 plus and Zn2 plus ion. After some time the concentration remains same, and at that time the voltmeter gives a reading of 0. Okay, the voltmeter gives a reading of 0. It keeps on decreasing, and after some time it becomes 0. So this indicates that equilibrium has attained, and at that point E of the cell is 0. So if this E of the cell becomes 0, I can write E naught is equal to plus 0.059 by N, and this whole concentration, since it is equilibrium concentration, is denoted by K. So what is this K here? This K is your equilibrium constant. Clear? Okay. Next we'll move to electrochemical cell and Gibbs free energy. So basically what happens, the electrical work, the work done by electricity, or the electrical work done is calculated by, in 1 second, is equal to the electrical potential multiplied by the total charge. Okay, the potential difference into the total charge gives you the electrical work. Now if we want maximum work from a galvanic cell, one galvanic cell is also electricity is produced, right? If I want maximum work from there, the process should be reversible. And what is reversible? A process which occurs very slowly, right? So then the charge has to be passed reversibly, means the charge that is passing here, the electrons that are passing here should pass very slowly. Okay. The reversible work done by a galvanic cell is equal to the decrease in Gibbs free energy, and therefore it is the EMF of the cell, and NF is the amount of charge passed, and delta G of the reaction. So from here we get a formula, delta G is equal to minus NF E naught of the cell. And from the previous one, what I have found out, so if you just see here, I have E of the cell at equilibrium. Okay, at equilibrium, E naught of the cell is equal to 2.303 RT by NF log of K, right? This is what I have found out. I have written this as 0.0591 by N. So what I can do here, you can see this one. What is E naught value? Delta G by NF, right? So I can write down this one as delta G by NF, right, is equal to 2.303 RT by NF log of K. So NF and NF I can cancel, this delta G minus can come here, so that is equal to minus 2.303 RT log K. Okay, so this will give me the formula of delta G. Clear? Okay, so these are the concepts that we have studied today: Nernst equation and equilibrium constant, and how it is related to Gibbs free energy. Now we'll do small numericals and we'll wind up this session. So calculate the equilibrium constant for the following reaction. So you have been given with all the values, E naught of the cell is given. So I can just do the calculation. So E naught of the cell is equal to 0.059 by N log of K, right? I have to calculate this one. So what is E naught of the cell value given to me? 0.46. Okay, this one can I write it as just a little bit of rounding off and write 0.06 for easy calculation. If I see the number of electrons involved, here it is 2 electrons, here also it is 2 electrons, so I have 2 log of K. So next I can solve it like this, as 2 ones are 2.03 and have 0.46 by 0.03 is equal to log of K. So I can just see 15 3s is 45, so 15 point something I'll get, or most probably I can have 46 divided by 3. So 3 ones are 3, I have 16, 15, then I have 1, 0, yeah, 15.3 I will get, right? So you will get 15.3 here, right? So what is the value here? I'll get 15.3 as log of K, okay, or round off to 15. So K will be somewhere equal to 10 to the power of 15, okay. So this is a rough value, you can do more detailed calculation. 10 to the power of 15 will be the value of the equilibrium constant. Next question, in the electrochemical cell reaction on increasing the concentration of Fe2+. So what will be the E naught of this cell? You have E of the cell minus 0.0591 by, we have n again 2 log of Fe2+ is there, then you have Zn2+, and these two ions are present on the left hand side or the product side, divided by Fe3+. So the question is saying that you are increasing the concentration of Fe2+, right? So that means what? This numerator will increase, this whole fraction will increase, this whole number will increase, and you are subtracting a bigger number, so EMF of the cell will decrease, right? The cell EMF will decrease. Clear? Next, we'll see calculate the cell potential. Okay, so you have to calculate a proper Nernst equation question. Okay, so let's first write down, just a minute. Yes, so first let's write down the equation. E of the cell equal to E naught of the cell minus 0.0591 by n. Again here I can see two electrons are there, log of, okay, log of product ion, that is Mg2+, divided by reactant concentration, that is Zn2+. Okay. Okay. Now you can see that Mg2+ and Zn2+ concentrations are equal, right? So that means these two will get cancelled. So I will have log 1 and log 1 is 0. So if that is, this part becomes 0, then this whole terms become 0, or I can say E of the cell will be equal to E naught of the cell, which is almost equal to 1.61, or you can have plus 1.63, right? Yes, so option number A is the most accurate answer here. Clear? Okay. So students, that's all in this class. We have covered Nernst equation in much detail. So just do practice questions from here, and in the next class we'll be talking about conductance of electrolytes and many more such concepts. So do subscribe the channel, and if you have any doubt in any question or any concept, put down in the comment section. I'll be addressing to that. Thank you for watching, and do not forget to subscribe the channel.